started. I know the camera is not running yet, but that's all right. Is it all running? Okay, good. So all sit down, no discussion later, otherwise we're going to run out of time. Okay, sorry. Okay, scalable topic models. So let me first explain a little bit what topic models are. And so what I could do is I could do some web page grouping by objects. So here's what happens. I have maybe 3 web pages. And if you've been to Singapore, you'll recognize all 3 of them. It's a good university, it's an airline. And that's a good place for going out for dinner chimes. So you can get some more pages. And maybe the Australian National University, Japanese, which is a nice restaurant in Berkeley, and then United Airlines, which is an airline. Okay, so you can group this, right? So you group it by airline, universities, and restaurants. And okay, so that's all fine, right? So everybody agrees that this is a good grouping. Well, actually, you could argue that this would be a better grouping. I could group by United States, Australia, and Singapore. Now, the trouble is, there's no way I can argue one way or the other and conclusively win the argument. This is exactly what I meant before with usually whenever you are in a situation where it's not clear which grouping is the right one, it probably means you're trying to solve the wrong question. This would be a bit better. So I could maybe tag it by Singapore University and food and airlines, and Australian University, USA Airline, USA Food. So now nobody will really argue with this, and if you really argue with it, you can add one more tag and everything's fine. So how can we get that? Well, the other thing that you might see through that is, even though I've now used a fairly small number of tags, I've managed to make things unique or fairly specific to each document. And at the same time, I've managed to stay reasonably parsimonious in terms of the number of tags that I'm using. So here's a bit of an explanation of what happens between clustering and topic models. So suppose I want to, group colors. Then what I could do is I could, group all the greens over here and all the blues there and all the reds there. And then if I have gray, well, it's kind of hard. So that sounds like a really stupid way of aggregating colors, but those of us who had the questionable pleasure of working on 8 or 16-bit color resolution displays would probably actually recall something like that. So at the time in your graphics card, there used to be something called a color lookup table, where all maybe 24-bit color depth colors were quantized into 8 or 16-bit whatever. And so if you had, for instance, a very green scene on your monitor, then you would use most of the green color spectrum to display that. And if you had something else, then things would change. And for instance, on Unix, you might then get the funny situation where, depending on where you move the cursor, the picture in the window that you're currently looking at started to look nice, and all the other colors looked weird. You might or might not have seen that, depending on how old you are. If you're old enough, you would remember this. Okay, so that is basically the algorithm that was running behind the scenes was essentially a clustering algorithm where for the entire set of pixels that I might want to display, I would go and find cluster centers that accurately represent the colors, and then I would map this again to a suitable display output and display it. So that's what clustering does. And I would have needed 2 to the 16 cluster centers to get something that looks halfway decent, even though I only have 3 primary colors, red, green, and blue. So, well, wouldn't it be much nicer if I could represent things this way? And as a matter of fact, basically every modern computer display does that. It just represents it by the red, the green, and the blue value, and everything's fine. So now I can decompose objects into prototypes, and in doing so, I get a much richer representation. So it's 2 to the 15, 2 to the 16 versus 3. And you would easily agree with me that, this three-dimensional vector space representation is much more accurate, much more user-friendly, much more understandable than telling you, well, this is the 799th green cluster, right? That means nothing. So what we want to do now is we want to get the equivalent of, so to say, primary colors, for instance, for documents. And if I have that, then this allows me to get a lot more content analysis for a document reasonably efficiently. Well, why would I care? So maybe 2 or 3 years ago, people started looking at distributional similarity of words. So one guy in that context is Patrick Pantel. And so he built similarity lists. And he would start his list and seed it with things like Ford, Lincoln, and maybe Toyota. Okay, fine. And by neighborhood similarity, the algorithm would then return back things like, okay, Mazda and I don't know, Pontiac and Mercedes and whatever. And it would also return things like Clinton or Bush, right? And you can easily see what's going on because it had Ford and Lincoln in it, right? These are also presidents. So this distributional similarity had no real means of finding out what the context was, what the longer range dependence was within the document. Now, if I knew that this document's about politics, I won't be returning the Mazdas, Toyotas, and Audis. If it's about, cars, well, then maybe Bush and, Clinton have no place there either. So, and you can play that game with cars further. I mean, there's Cougar, there's Jaguar, and so on, and, then you get lions and so on, and then you get lion, leopard, and so on. Then you get snow leopard, you get apple. So you can easily see how you can break those lists in interesting ways, because quite often keywords have more than one meaning. So one thing that, for instance, I found out by applying something like that to documents is that the word Jaguar has at least 4 meanings. So we probably know about the operating system version, about the animal, and about the car. Turns out there used to be, once upon a time, an Atari console called the Jaguar, right? So that's the kind of things that you can find out easily by building such models. Likewise, you can find out what topics various documents are about. Okay, so how do we get it? So let's just look at clustering, right? So we have our prior. That gives us the cluster probability, the probability with which particular cluster occurs. And then, that's my label. So I draw that cluster label from it, and then I draw the instance. Now, all I'm going to do is I'm going to put the red box around it. That's the entire difference. And I'm going to call the clusters here topics. Right? Just rename and red box. So what's happened here is I've basically now said that, for instance, within my document, the topic probability, the topic distribution is different between 2 different documents. So one document might be about cars, the other one might be about politicians. And then I draw, this is a simple bag of words representation, there are more intelligent ones out there. I draw, as I go along, well, which topics are going to be for that particular word, and then I draw from the supply of words for that topic. And I go through. And this is latent Dirichlet allocation. So that simple red box creates an extremely well-cited paper. They did a lot more things in that paper, don't worry. But that's conceptually all you need to remember. Let me explain it to you in a third way. So we might have, the cluster topic distribution. Then I get the membership of, which words go into which cluster. And that product between those 2 matrices gives me documents. So I can either view it. So for clustering, I just have a 0-1 matrix here in the membership. But the entire document belongs to one cluster or not. In topic models, I have a stochastic matrix. So all those guys sum up to 1 per column. In LSI, they are just arbitrary matrices, both of them. can have non-negative matrix factorization, where both matrices have non-negative entries. I can have a different meaning for that equality, namely, for instance, a logistic. And then I'm pretty close to being back at the topic model. So tiny modifications here have given rise to entire tribes of document modeling, well, paper factories. Yes?
Isn't there also still a word distribution over topics, like one more part of the LDA?
Yes, that's here. That's this model here. So you have, how do I describe the document? How do I describe the words? And different assumptions and conditions on these matrices give you different paper factories. And people with great aplomb have taken an idea from one of those constraints, moved it over to the other one, republished it, and gotten very well-cited papers out of it. Okay. It's also a way of getting papers. But what I wanted to explain is that you can view it as a clustering model where I just put another plate around it, or as a mixture model of, so to say, primary colors. And they all three amount to the same thing, namely I'm now describing an object as a combination of constituents. So the question that is very common is the following. People would ask me, so what's the difference between this and probabilistic clustering, right? After all, I might take my document and I might say, well, with 0.5 probability, it's maybe about cars. With 0.3, it's about politicians. And with 0.2, it's something else. So that means you're not quite sure which one the answer is, but you know that there exists a true answer, that it's either a car or a politician or something else. Okay. So that's like there's the old joke about the Bayesian who's sent to a dark room, and he's told there might be a horse or a donkey in it. And so when he comes out, you ask him, what did you find? And he says, well, I found a mule. And that's basically allowing for the interpolation between both. Right? So there's a difference between saying, well, I'm not really sure whether it's a horse or a donkey, or whether I say, well, I'm fairly sure it's a mule. And it's the latter type of models that we're looking here with topic models. Okay. Sorry for belaboring that point a lot, but I've seen people get it wrong many times. Okay. Topics in text. So or maybe I should quickly walk you through that model. So what we have here is we have a Dirichlet prior, which is a prior for the topic probability within the document. And then I draw from that topic distribution, the topic of a particular word, and I draw the word from the corresponding verb model. That's the entire graphical model. Here's an example. That was in the LDA paper. I mean, the name is sort of a little bit unfortunate because it also means linear discriminant analysis, right? But basically, they took a document. They actually took a large collection of, I think in this case, New York Times documents, and color-coded all the various topics. And you can see that maybe the green bits are more about, corporate finance, and then, maybe blue is about Hearst and all social things, and then the red bit is about culture, and then the black bits are about, whatever else. And it's not perfect, but it gets it sort of kind of right. And it was one of the first examples. It was very surprising that this could be done quite as well. So how do we actually perform inference? So let me show you the collapsed Gibbs sampler. So here's the model again. I've just made things a little bit more explicit. I've just said, well, look, here is the word distribution per topic. Here's the language prior. You probably shouldn't pick a uniform one, even though people typically do. Here's the topic prior. Again, it probably shouldn't be uniform. So topic probability per document, that's the topic label, that's the instance. And so now, the joint distribution over all these parameters, given the hyperparameters, is, product over all the topics, product over all the documents. And here's the product over all the words in the document, namely the topic ID and the words. So it's really just this thing written out. I haven't really specified anything further yet. Any questions so far? Yep.
What are the timing that, in your organization, have you fit these models or similar models for the data that you have?
Okay, so this model is plain vanilla without time. You definitely want to add time to any experiment with real data, because, for instance, topics change, right? So, like elections coming up every 2 or 4 years. There are, particular events that occur at some times, like you might have a stock crash. People's interests change over time. What various topics mean changes over time. And you want to incorporate all of that. And I'll show you a little bit of such a model later on. But I first want to make sure everybody really understands the basic vanilla model. And then we'll look, time permitting, at lots of different variants of amazingly fancy things you can do to go beyond this. But before I go beyond the basic model, I want to make sure everybody understands how you can do inference in the basic model efficiently. So what you could do is you could basically go and sample over those psi's, the thetas, and the z's independently, and you iterate. That's a Gibbs sampler. Now it turns out that I can actually integrate out the psi's and the thetas. It's by these variables here. That's exactly why I stressed so much the collapsed representation for conjugate random variables yesterday, because we're making use of that right now. The point is, if I get rid of some variables, the rest is tightly coupled, so my sampler mixes faster. I pay a price for that. The price is that now things are much more dependent on each other, but at least if I were able to perform the sampler efficiently, it would mix a lot faster. And as a matter of fact, that is what Griffith and Stivers did in their paper in 2005. They showed that the collapsed Gibbs sampler is actually very effective. So, to drive that point home, this is slow, excruciatingly slow. Yes, you could implement that fairly easily on MapReduce, and you could do 1,000 MapReduce iterations, and you'd get something. So here's a better way. I collapse. Namely, it turns out I can basically get rid of these thetas and psi's, and now I get something where I just have all the p of zi's given alpha, and Cij is given alpha, and I have the p of xij given Cij and k. So in other words, if I knew what these variables are, the rest of the expressions actually can be written out in closed form. Then I just go through one topic assignment variable after the other in all the documents, in all the words, and sample. Right. So that looks great, right? It mixes fast. And so here's the math for it. It's very fast. So let's just look at the math in a bit more detail, because it actually tells us interesting things. So these are, if you work out the algebra, the corresponding probabilities. Well, so n minus ij or minus I just means, well, that particular document or that particular word left out. That's what the minus means. So ignore that minus bit for a moment. TD means account for a particular topic for a particular document. That's for a particular document. That's for a particular topic. It's a particular topic and word combination. Okay. So what I get is here, the probability, the collapse probability, is basically just the number of times I've seen a particular topic in a particular document, plus Laplace smoothing. And in the denominator, I need to divide by the sum over all the topics and all the smoothers. Okay. Nice thing that happens here in the denominator is that the number of words per document doesn't change, so I can actually throw this away. Then here, well, the emission probability of a given word for a condition on that I've chosen a particular topic, right? It's just the number of times that particular topic has occurred for that word, plus the language smoother divided by, now I need to sum over all the topics again, n minus I of t, so that's the number of words that have a particular topic assigned to it, plus then the smoother just summed over it. Okay. So you can go through a bunch of ratios of gamma functions to get to this. You can also derive it approximately in first order by just doing a Taylor expansion on general conjugate priors. If we have a bit of time, I might just show you that derivation later, but I don't want to confuse it too much now. But what it means is you're really just using a best effort estimate of the corresponding word and topic probabilities. And each time you resample a topic assignment, you update all your counts. Are there any questions at this point? No, not you, because you've already asked 5 today. So you can ask in the break. Somebody else. So, I'm sorry, but somebody else. Any questions? Yes?
I probably just forgot this, but how do you just initialize? So where do you get your topics to begin with? Is that the prior, or do you kind of initialize some random topics and then?
Okay, that's an excellent question. So the dumb implementation is you just initialize all the topic assignments at random.
Just random words
No. You just basically go through your documents, and for each word, you randomly assign a topic to it. That's the equivalent of the random cluster assignment. A better way is to go sequentially through the document, start with essentially an empty table and assign things as you go along in more of a sequential Monte Carlo fashion. There are actually sequential Monte Carlo algorithms that get away with essentially one pass through the document. And I'll show you later on, tomorrow, time permitting, how you can do fairly fancy document clustering this way. But that doesn't parallelize quite as nicely. So, for the, yes? So it's not an exponent here. This is just leave this guy out. So minus aj means just leave the word at position j at document I out of my count. Otherwise, we will get really horrible numbers, yes. But I just don't know how else to write it, and everybody in non-parametric base seems to have agreed on that weird notation, so I'm just using it too. Yeah, it's a very weird notation. I agree. Any other questions? Yep.
Is it possible to use MapReduce in this collapsed sample?
No, not efficiently. So there are papers by Max Welling, and I'll show you that on the next slide, that use the equivalent of MapReduce for inference in this case. And the algorithms don't mix very well, and they would actually run fairly slow. So we get about, I would venture, a 5 times, maybe 10 times speed up by not using it. And I'll show you now exactly how those inference algorithms work. So let's just look at the simplest case. And so what could I do? I could just do, for 1,000 iterations, 1,000 Gibbs sampling iterations, for each document, for each word in the document, do resample the topic for the word, update the local document topic table. That's easy. It's a local variable, so I could do that in parallel. Update the CPU local word topic table, right? But the problem is I also need to update this global word topic table. So this is already an issue if I have, several cores. I'll need to deal with locking here. This is the much bigger issue that the global word topic table might need to be synchronized with a different machine. And those red bits kill parallelism badly. So if we think about it, actually, maybe things aren't quite as bad. This is the fastest changing set of variables, and that's local. That's good. That one I can probably keep in sync fairly efficiently, so I can deal with this. This is the big issue. Now, if I update the global topic word table only after one pass through my entire document collection, which might be millions of documents, things will have probably diverged a lot, and so I get very slow conversions. And that's exactly what we're going to deal with. So here's what pretty much everybody else but us does. They update this locally fine, and then they wait until they are through all the documents and they update the global table. And here's exactly what I explained. So you have this variable here. So this one is slowly moving, so that's fine. I mean, the global count of words that are assigned to a topic isn't going to change very much if I change 1 or 2 words, right? So, I mean, we're talking about billions, maybe trillions of words. This changes really rapidly, but that's also fine because it's local per CPU core, so no worries. This changes moderately quickly, and unfortunately, this one needs to be synchronized as aggressively as I can. And this step here doesn't do it. So the problem is the tables get out of sync. It's really memory inefficient because you need to keep local copies around per thread. It requires blocking because you basically sample. Then you stop everything. Then you communicate. And if some machine is stuck, then, well, you're just stuck. And then you wait for the network until you've sent all the data forwards and backwards. And then you continue your computation. This is really bad. So how can we deal with it? Well, here's what we do. We basically, in parallel, update our local table, and in parallel, continuously keep on updating the global word topic table. So what we're doing is we have 2 threads. One that locally within the machine keeps on updating statistics between the different cores. And that's easily done, as I'll show you in a moment, by just deferring all the updates to a single updater thread and having all the sampling being done, which is really the CPU-heavy part, by different cores. And then having another thread running in the background that synchronizes our local statistics per machine with all the other machines. So unlike MapReduce, where you stop everything, then you talk, and then you keep on doing things independently, this is an extremely chatty procedure. But by being extremely chatty, I maximize my network throughput, and I get much faster convergence. Furthermore, and that's quite nice, suppose I manage to partition my documents very well between, say, 2 different languages, then each machine only needs to know its own local counts and only synchronize them. Yeah, question?
I don't know if this is a dumb question, but where is the global table stored?
Yeah, excellent question, and I'll actually have a few slides on that very issue. That global table is being stored in a distributed fashion, so that's exactly this distributed star that I explained on the first day, where each machine has a small portion of it. And in doing this, we'll get perfect bandwidth scaling with more machines. Thanks for that question, because that's what we're going to talk about now, architecture details. Any other questions so far? Okay. So here's what we do. That's for a single machine. We basically read the tokens and topics from disk. The tokens, so basically the words, and the topics are actually in separate files, and they are just merged. The reason why we do this is because at the end of the day, the tokens don't change, but the topics do, and we only write the new topics out. That doubles our write performance, because we only write half the amount of data. Simple engineering, but speeds up things. Okay, so this is now one filter that just combines everything. Then we have many cores. Each of them attacks one document and resamples it. Then after it's done this, there are going to be updates to the topic counts and topic word counts. It creates a message that's being sent on, and after some diagnostics, it goes into this updater, which now updates our count tables. The advantage is this only needs read logs. This one acquires write logs. You can put all sorts of other things into that, where you can do intelligent upstream conditioning and so on. I'm not going to go into detail here, and then you write to disk. This way, most of the state of the sampler is on disk. Just reading it in, updating, writing it back out on disk. So if my machine crashes, as long as the disk is still there, I'm in good shape. I need a lot less memory because I now don't need a separate state table per sampler, but only per machine. Otherwise, my memory requirements would be linear in the number of cores, which would be really awful. And all I need to do is just, I stream the documents through memory. This is something for which, for instance, the Hadoop file system is really good. So we can use that. That's single machine. That's a lot faster than what you, for instance, can find in Mallet. Code in Mallet is extremely beautifully written, and we use some of their techniques. But the architecture is different. Because in Mallet, basically, each thread has its entire own state table. Then this is what we do between different machines. We use a library called ICE, which is written by the people who wrote Corba, and then got disgusted about what the mess it was, so they did it cleanly. And it basically, if you need to do multi-processor programming, do not use MPI or anything like that. Use ICE. It's much nicer. It basically is an interface definition language by which you define, OK, these two processes need to talk to each other, and this is the data they send. And it deals with all the threading and synchronization and marshalling the data and so on in the background. So you don't have to do it. It makes for very compact code. It's a beautiful library. And now what we do is we have this distributed key value storage. There we still used memcached, but now it's actually ICE. So memcached didn't have a particular thing that, namely, didn't have versioned writes, and the message passing turned out very awkward. So by switching to ICE, we got about a 10-fold speed up on the communication. And we basically store the key value pairs on different machines. And so we don't even need a joint dictionary. Each machine just grabs the words that it knows of, nothing else. And now we use network and disk and everything simultaneously. This is what it really looks like in practice. Basically, each machine that's running the sampler also stores a small portion of the data, and all the other machines talk to it. So now you get perfect linear scalability in terms of the network. Okay, that's the basic idea. And now we are using the disk, streaming from disk, the network by synchronizing in the CPU simultaneously. Deadlocks aren't a major issue because you might have 1 million words. And so if I have 1,000 machines which synchronize, chances that 2 machines will hit the same word aren't that high. Yes?
So what happens if the machine dies? Is it all as in
Perfect question. Very good question. This is actually at the moment our biggest bugbear. If a machine dies, you pretty much need to restart the sampler from the point where the machine died. So it takes down the entire system. This is extremely awful, and I don't have a very good solution to that. Fortunately, our machines are fairly reliable, so it usually doesn't happen, but there's a hot start built in. And it's not too bad, because basically if you have maybe 1,000 sampling iterations, hot start from disk takes as long as one of those sampling iterations. So if you have maybe 5 machine failures for 1,000 iterations, well, OK, it takes the equivalent of 1,000 5 times. But yes, it is an issue. The reason why we can deal with it reasonably efficiently, because after each machine is done, it just writes its current state to disk. And our hot start is in such a way that it actually aggregates and assembles the joint state table by the backups from disk. And the good thing is that the state is in such a way that it's decomposable. So you don't end up with invalid state by just aggregating partial states from different machines. Not all systems will allow this. But in general, anything that is an exchangeable statistic of data will let you do this. So in other words, min, max, and average are good operations for that. However, min and max are not good operations for updating statistics. So in practice, basically, anything that's a count or an average is good. Other things are not so great. OK. Any other questions? By the way, these are great questions that you guys are asking. Oops, what's that? Okay, good. So then we move on. So how to make it work? You randomly initialize. You need some failover. Basically, you constantly write to disk. That's exactly the issue. And yes, you had that issue. We need to restart from a checkpoint even if a single machine dies. You can fairly easily extend it. We can get better language models rather than just unigrams. We can have n-grams. And the largest published results for topical n-grams, I think, is a few thousand documents. And it easily deals with millions, tens of millions of them. That part of the code is not released yet. You can condition on-site information, upstream or downstream conditioning. So basically, if I know for a document who wrote it, I will have a pretty good idea what it's going to be about. I might have, information about some words being similar. So for instance, suppose I have two languages and I want to make sure the topics are coordinated. Then I could, of course, use a translation service and run the topic model in one language and just map it back. Or I could assume, and at least I have a dictionary. Now, dictionaries are not particularly good because you can get things like, for instance, the word crane in English is both the construction device and the bird. And for instance, in German, that's Kran and Kranich. They're two different words. Actually, in many languages, it's two different words. So what that actually means is that there are not necessarily one-to-one mappings between different words. Or for instance, I might have WordNet, which tells me that two words in the same language are similar. And therefore, also their topic distributions ought to be similar in general as a prior. So I can use this to smooth over topic distributions between words, and that gives me better downstream conditioning. That's something that James Pedersen and Shravan and I did last year for NIPS. You can have a time-dependent sampler for the user model, and we'll be talking about that a lot more. Brief comparison. Yeah, basically, we do most of the things, and that code is now available on GitHub. It's fast. So these are slightly older results. By now, it's quite a bit faster. Not going to go much into detail. I think that's probably an interesting figure. Throughput in terms of number of documents per hour. These numbers, these are fair. These are extrapolated because, as a matter of fact, one of the Google LDA papers, they run 20 or 30 sampling iterations, so they are nowhere near convergence. I have no idea how long their code would take to converge. These are optimistic estimates because they are non-public data sets and with a way too small number of iterations. So if somebody can give me more accurate figures there, that would be useful. Just to conclude this a little bit with some design principles. So one thing that we do is we replicate variables. So if I have a global shared variable between different machines, I make a local copy of that per computer and I synchronize. And the synchronization happens through a distributed key value storage. In addition to that, the particular details are that I basically put the onus of the bookkeeping all on the computer that has the local copy, not the global version. So this is a bit different from message passing. Remember, in message passing, we had to divide out the incoming message from the recipient. Here, I leave it in, and I tell the recipient to deal with that. And for averages, that's easily possible. And I synchronize all those copies asynchronously. And of course, this is an approximation. It's an open research question at the moment to prove how bad an approximation this is. And I suppose I'm pretty much out of time. So this is just the asymmetric message passing, what I mentioned. Out of core, well, you just stream things through. This part actually is more or less exact. And that's it. So I think I'm horribly out of time by now. Do you have 20 more minutes?
No, then until 4:30.
Until 4:30. Good. Yay! OK. Well, let's go to advanced modeling. Or do you want to know more system stuff? Who wants to know models? Who wants to see models? Okay, systems? Okay. Okay, good. Okay, I think that's... So here's what you can do. You can, for instance, say, well, hey, actually this Dirichlet prior is maybe not the best prior for, just a topic distribution. So, rather than having a Dirichlet distribution, you can just have something like a penalized logistic where I have a Gaussian prior. Right? That's the simple thing that I showed you before. If you applied the simple idea to topic models, you would have gotten one of the most cited papers in that context. It's called the correlated topic model. See, simple idea applied to a new problem, well-cited paper. You could have a hierarchical structure over the topics, and you could impose that. That also gives you an interesting paper. You could have modifications to the document structure. So, of course, bag of words is what we used so far, but you could actually have engrams where you say, well, look, there's a sequence of words, and they depend on each other, and I want to make sure that they're overall properly modeled. I could say, well, actually, we have Markov chains, and we model them. Yes?
Doesn't that lead to sparsity issues, though, or estimation?
Sparsity, yes, absolutely. So if I have engrams, I'll have very few of them. And this is actually good, because if I had way too many engrams, they would run out of main memory. So all those algorithms run pretty much at the limit of what you can squeeze into main memory. So you have to do actually lots of really clever memory management to fit this vector into memory. So if you think about it, you might have 1,000 topics. You might have maybe 10 million words. Oops, you're out of memory, right? You're not out of memory if you store the variables efficiently. And yeah, so am I already eating into your time?
No.
Good. And so what you do is you basically take a sparse vector. You don't quite know which topic and which word combination is a priori going to be sparse. You allocate it sparsely, and then whenever you see the vector is too sparse, you halve the amount of storage allocated. If you run out of it, you double the amount of storage allocated. So that's a simple guess and double strategy, which is within a factor of 2 optimal, and it ensures that basically you're not going to do memory allocations too frequently, because mallocs are slow on a computer. Then you can use a lot of side information. So the upstream conditioning, for instance, you can use the information who wrote the document. You can do the downstream conditioning, which is what I mentioned before. Basically, what do the words mean? They're, after all, not in Klingon, but we know some more things about the words. And also, I can use label information. So if I know that particular documents correspond to particular categories, well, I should be able to use that in inferring what label distribution I should see. Okay. So let's go through it in a bit more detail. So the correlated topic models are basically, we can only model which topics are hot. That's what the Dirichlet distribution does. It doesn't really model the relationships between them. And so, well, we expect that certain topic combinations are more frequent than other. And so I use just a log normal distribution as a prior. What then happens is I lose all the nice properties of conjugacy, so I can't do the collapsing efficiently anymore. The inference is a lot harder, and I can do variational or whatever. Right? So let me show you pictures. That's what the Dirichlet distribution does on topics. It's just, centered somewhere, but, there's only a fairly limited set of shapes that I can get. And if I use a log normal prior on topics, I can get much more interesting correlations. It's that correlation matrix that makes the stuff interesting. And then if I do this, I can, for instance, get similarities between topics. And if you download my slides and squint at it, you'll see that this makes sense. And you can produce beautiful, pretty pictures with it. And yeah, this is a very well-cited paper. It's a nice idea. I mean, in hindsight, it's obvious, but to think about it was not quite that obvious. That's actually the case with a lot of things in well, a lot of areas, amongst others machine learning, the concepts that underlie a couple of very successful models are very simple. What this also means is, if you're working on a problem and the concepts that you require are very complex, then three possible things are happening. Either you're doing something amazingly deep that nobody else has done before. That occasionally happens. So there are some proofs that just need to be complicated. Or you're making things way more complicated than they ought to be. And you should actually just not do this. Or you're doing very good engineering. You're solving a very specific problem in a very specific manner. And obviously, you want to avoid the case where you're just adding complexity for no good reason. Unfortunately, a lot of papers are of that form, where people propose modifications to models which give them an absolute improvement but make things a lot more complicated. So a good yardstick is, ask yourself, is that additional complexity actually worth it? Will somebody else read this paper, say, well, this is the right way to solve an important problem, and replicate the steps and implement, re-implement, redo what I've done? If that answer comes up with no, stop there. Unless somebody's paying you to solve that specific problem. But that's a pretty good quality criterion for, what to look at. Okay, some more correlated topics, fine. Pachinko allocation. This is, I think, a slightly nicer way of looking at correlations. In this way, we don't get outside the conjugate family, but what it basically does is it says, well, let's look at the hierarchy of multinomial distributions. So by the way, who knows what Pachinko is? You need to go to Japan. Okay, so a Pachinko, so you need to go to a Pachinko parlor, and basically what they have is they have this big board of, so it's in a machine, it makes a hideous amount of noise, but basically they have those pins there, and you roll a ball on top of it, and it goes through, it's basically like one of those Bernoulli systems. And you can, in some ways, control where the ball starts, and sometimes you can control it in some other ways later on, but it's pretty much random at that point. Depending on where the ball comes out, you might get more balls back or not, and usually you start with a big bucket of steel balls, you end up with a pretty much empty bucket of steel balls, unless you're really good at it. And by now most of those things are computerized, so talent doesn't help you so much anymore. So that's Pachinko. This thing looks awfully much like a Pachinko model, right? So each of those are like nails, and there I decide, okay, where I'm going to go. Now, what does this have to do with document modeling? I could, for instance, decide, okay, today I'm going to write a paper in computer science as opposed to statistics. Now, in computer science, what's it going to be about? Maybe machine learning and maybe a bit of systems. Okay, so we move down here. So maybe I've picked the systems part. Well, what do I write about in systems? Well, maybe about caching, so I do this. But maybe, I could have also done a statistical analysis of caching, right? So each of those paths would have been fine. Now, that's a nice way of looking at a hierarchical dependence of various topics. And of course, I could also allow for shortcuts, and then the inference becomes an even bigger mess than it already is here. So it's a beautiful paper, unfortunately, again, not implemented at scale. But it will give you hierarchies. That's what you get. If you squint, you see that stuff makes a lot of sense. These are all computer science papers. That, for instance, there's a good combination between distributed systems, parallel processing, networks, and, of course, it's a paper. So the central topic that occurs everywhere is that abstract-based approach paper present. Each paper would have those words in it. You could also do something about speech recognition. So you'll have speech recognition, grammar, dialogue, and paper, right? Or Relational databases, data mining information on the web, and paper. And so you can see those connections that actually make a lot of sense in terms of, which topics would occur in which combination for papers. And, you might have networks occurring, for instance, in the web server part and also in the parallel processing part. So it's kind of nice. And so you get those hierarchies. You can do that too. So that's basically where you have hierarchies over words. And I can get topical n-grams. And I think by now my time is really up because I don't want to push that delay on further. So all this does is basically just assumes that the next word doesn't only necessarily depend on the topic of its associated topic, but also what the previous topic was and what the previous word was. And then I have a switch variable which tells me, okay, am I going to break the sequence here or not? And of course, that works better, right? Because otherwise they couldn't have published a paper about it. So you get basically, if you look at the topics, they make more sense if you have pairs of words rather than single words. And yeah, we have that implemented at quite larger scale. And this is what I want to conclude with for today. Tomorrow we'll be looking at a lot more models. And then in the end, if we get lucky, we might do a little bit of undirected graphical models. Any questions? Yes?
Sorry, Mr. Could you say you were going to talk about the time dependence?
Yes, I will be talking about that tomorrow. So they infer the switching points in addition to the topics and everything. So this is the nice thing about graphical models. Well, you might think, well, actually it depends on yet another thing. Okay, good, we add another variable. Now, will it work? Well, that depends a lot on whether you can find an efficient inference algorithm, because sometimes it's very easy to write out a graphical model and then much harder to actually do the inference part in it. Or it may actually take too long, so you can only carry it out on excruciatingly small data sets. And one example of that are, for instance, the topic link models of, that were proposed in some UAI paper, I think in 2008 or 2007, where they could process a whopping 2,000 web pages from Wikipedia, which is a few orders of magnitude smaller than what you would care about the internet. Let's say probably about 6 to 8 orders of magnitude below. But at least you can do it. That's the general idea of what can be done. Any other questions? Okay, good. Then, well, thanks for your patience today.